I'd like to talk to you about structure in the inner core using two different sorts of seismic data. First, body wave data, which we've already heard about this morning, and secondly, normal mode data. So a very brief primer to begin. Where are we looking? Earth's inner core was first discovered by Inga Lehmann in 1936, and she used seismic body waves generated by an earthquake and detected at the far side of the Earth. She found seismic arrivals which didn't match what one would expect if there was just a liquid outer core. Instead, she found arrivals in the shadow zone of the liquid outer core and guessed that there must be something else in the centre of the Earth. She pretended that the Earth was very uniform, that rays travelled as these perfect straight lines, and estimated that there was an inner core with a radius of about 1,400 kilometres. Despite her approximations, this was a very, very good calculation. We know today that the inner core has a radius of about 1,220 kilometres and is composed of a solid iron-nickel alloy. I'll briefly touch on what we think the inner core is made of, because I know that speakers later today will talk about this in much more detail. We know that the inner core is mostly iron by thinking about both density and inertia of the Earth. In fact, it's 90% iron-nickel with 10% light elements. And these light elements are a matter of some debate. Is there sulfur? Could it be silicon, oxygen, hydrogen, carbon? The list goes on. Again, the crystalline structure in the inner core is currently unknown. Whether we have a body-centre cubic structure, a face-centre cubic structure, or a hexagonally close-packed structure is something which, as seismologists, we can't yet tell you. And when we consider the question of light elements, the problem of which crystalline structure we prefer becomes even more complicated. If we don't know a great deal about the composition of the inner core, it also has another unusual property, and this is inner core anisotropy. Inner core anisotropy was suggested in two back-to-back papers to explain two different seismic properties of the inner core. The first is the variation in body wave travel time with the direction of ray travel. So waves which travel north-south through the Earth will go faster than those which travel east-west. So polar rays will be faster than equatorial rays. The second seismic observation was the anomalous splitting of Earth's normal modes of oscillation, and I'll talk more about this later. If we can observe the anisotropy, one must ask, why is it there? What causes it? And the main suggestions are crystalline alignment due to either thermal or magnetic gradients in the core. This structure could develop during crystallization as the inner core grows, or it may happen after crystallization. This cartoon is taken from work by Yoshida and co-workers. He suggests that inner core anisotropy is due to faster growth of the inner core at the equator, and he's modelling uniform anisotropy throughout the inner core. If the inner core grows more quickly at the equator, it will not be spherical, but will instead have this oblate shape. To keep the hydrostatic forces in check, it will then deform, causing an anisotropic structure. An alternative suggested by Koamieli and co-workers, and also by Singh and co-workers, is that the inner core contains planar or ellipsoidal features. For example, Singh suggested that if we have elliptical features in the inner core, this may explain the anisotropy we observe today. The first seismic way we can investigate this anisotropy is to use body waves. PKPDF is the main wave which goes through the inner core. It's a P wave, a compressional wave. And as you can see, it's generated by an earthquake, travels through the mantle, the outer core, gets to its deepest point in the inner core, and then comes back up to the surface. PKP-BC is generated by the same earthquake at the same time, but travels a slightly different path. It goes through the mantle, gets to its deepest point in the outer core, and then comes back up to the surface. PKP-AB also gets to its deepest point in the outer core, but arrives a little bit after BC, and it turns more shallowly in the outer core. You can see that the paths are very close together of all these waves in the crust and upper mantle. And if they're generated by the same earthquake and recorded at the same station, then as seismologists, we don't have to worry about the earthquake being mislocated or mistimed. We can look at the difference between the arrival times of the PKP-DF and the PKP-BC, which should tell us just about structure in the deep earth. Or we could use PKP-DF and PKP-AB, and that will also tell us about structure in the earth. So finally, I can show you some seismograms. The wave which turns in the outer core, PKBC, is marked on and lined up with a prediction. We would then predict that for this earthquake and this station, PKP-DF, the inner core wave, would arrive here. But that's not the case, it arrives later. So the inner core is slower than we would expect for this equatorial path. On the other hand, for a different earthquake in a different station, we find that the wave which goes through the inner core is instead fast. So this equatorial path has a slow inner core, and this polar path has a fast inner core, and these two seismograms are part of a large data set which provides evidence for inner core anisotropy. Briefly, just some terminology. If we have a wave which travels north-south, it's polar, and it has a small ray angle, zeta. If we have a wave which travels east-west, it's equatorial, and we'll have a zeta which is close to 90. So now we can go ahead and compare the times we measure with the angles. The two data sets sample slightly shallower in the inner core and slightly deeper in the inner core. And I show for you here the travel time anomaly as a fraction of what it should be compared to the ray angle. So we have equatorial paths and polar paths. And the polar paths are fast. So we have inner core anisotropy, just as we would expect. There is a problem, though, which is that not all of the polar paths are fast. Instead, some of the north-south paths appear to behave just like the equatorial paths. So the anisotropy we can observe both in the shallower data for the inner core and the deeper data for the inner core is not uniform. We can look in more detail at what's happening to these data. And what I show you now are the polar paths in blue, the non-polar paths in yellow, and turning longitude, so the point at which that wave reaches its deepest point in the inner core. So the western hemisphere is here, the eastern hemisphere is here, France is somewhere around here. And what we find is that the polar paths are not always fast, but those which are fast are in the west. Those which are not fast are in the east. We see almost a sinusoidal pattern, especially in the deeper data, with fast paths and slow paths uniformly, smoothly varying with turning longitude. If we look at the equatorial paths, again we can almost see a sinusoidal pattern in the opposite direction. So in the west, equatorial paths are slightly slower than those in the east, and this is again true for both data sets. And finally, we can look at this on maps, and again we see exactly the same features. For the polar paths, we see a fast west and an eastern hemisphere, which is just as you would expect with no anisotropy. We have two distinct hemispheres in the inner core, which affect the anisotropy we can observe. It's therefore important to find out more about the boundaries between these two hemispheres. In particular, we want to know where the boundaries are located. So I've carried out some work where I've systematically searched for the locations of the boundaries between two hemispheres. I've seen how well each particular boundary location fits the data, allowing both hemispheres to be isotropic or anisotropic as the data would prefer. And I found best fitting hemispheres where there are light colours, and the best fitting boundary locations are at 14 degrees east and 151 degrees west. To give you some idea of the error on these measurements, I show you cross-sections where one boundary is held in the same place and the other boundary is allowed to move sideways. And you will see that the preferred boundary location at 151 degrees west has quite a wide error bound on it, whereas the preferred boundary at 14 degrees east has a much lower error boundary on it. We can see, though, that we definitely fit the data better if the two boundaries are approximately 180 degrees apart, but not quite. When we use the best fitting boundary locations, it's immediately apparent that we have done a good job, that we see the anisotropy in the Western Hemisphere fitting the data very well. So we see about 4.8% for the PKP BC, PKP DF data. Whereas in the Eastern Hemisphere, we see significantly less anisotropy. A small value of around 0.5 to 1% fits the data best. And if we divide this data up into the depth ranges where the waves turn, so if we're starting off with the shallowest data up here and deeper data up here all the way down to these sorts of numbers, then we see hemispheres in the anisotropy at each depth range for this data. PKP-AB DF data, the second of my data sets, samples deeper in the inner core, but the problem we have is that the AB and DF rays are further apart from each other, so we see more scatter in the data. The errors are larger. However, this lets us look right down to the deepest parts of the inner core, and for this data panel, we see data which turns below about 360 kilometres under the inner core boundary, so in the innermost half of the inner core. When we get to these much greater depths, we start to see that the Eastern Hemisphere looks nearly as anisotropic as the Western Hemisphere. It's therefore likely that these hemispherical differences may start to die out towards the centre of the inner core. Unfortunately, we have insufficient data to tell us about the innermost inner core, which Annie talked about earlier. So when we use body waves, we see these two inner core hemispheres, an anisotropic Western Hemisphere and a nearly isotropic Eastern Hemisphere. But if the structure in the inner core is so large, we would hope to be able to see it with other sorts of seismic data. And in particular, we would hope that normal mode oscillations would tell us about the structure in the innermost inner core. So here I show you a couple of little cartoons about how normal mode oscillations look. Obviously, they're not this large when an earthquake happens. But when an earthquake does happen, the entire Earth starts to vibrate, and it shakes at very different particular frequencies. These particular frequencies change depending on the structure in the Earth. So different structure in the Earth will cause slightly different frequencies of oscillation. And different normal modes are sensitive to the velocity and density of different depths of the Earth. So some modes will only sense velocity and density structure in the shallow parts, but some normal modes are sensitive to the velocity and density structure at the very centre of the Earth in the inner core. I show you here some data and a synthetic spectrum for one earthquake. We see changes in frequency, and at particular frequencies, we see that the Earth vibrates after an earthquake. The synthetic spectrum is shown as the dotted line, and you will see that for each oscillation, we have a single peak, one peak for one oscillation. But when there is asymmetric structure in the Earth, so it doesn't behave as just a 1D smooth Earth, then what we find with the data is that there are often several peaks. A good example of this is this mode here, marked as 3s2. If the Earth had uniform structure, especially if the inner core had uniform structure, then we would expect to see one peak in our spectra, but instead we see several peaks. This happens because the singlets which make up the mode, which are very, very close together in frequency and have the same sort of oscillation but slightly different arrangements on the surface of the Earth, these singlets would have the same frequency, but the structure in the Earth causes them to move slightly apart. This is called the splitting of normal modes, and in this case, structure in the inner core causes this mode to split. When we think about how to compute the normal modes, there are two different ways we can do it. We can use the self-coupling approximation. This tells us that when a mode splits, we only have to think about interactions within that one mode due to structure in the Earth. If we were to do full coupling, we would think that structure in the Earth could cause one mode to interact or resonate with another mode close by. This would let us see odd degree structure, particularly degree 1 structure in the Earth. It becomes a much more difficult computational problem. If we just have to think about one mode interacting with itself and splitting, then we just have to think about doing the calculations marked in these blue boxes. And these would be relatively straightforward. If we allow full coupling, we have to allow this mode to interact with this mode and think about what interactions we may see between the two modes. It's obviously a computationally more difficult problem, but it lets us look for inner core structure if we do full coupling. So what we can do is take existing models of inner core anisotropy, and we can chop them in half. We can put anisotropy in half of the inner core and not in the other half of the inner core. We can allow the modes to couple if they want to, if the structure makes them interact, and we can see what happens. We can see if we would even be sensitive to structure of this sort. And I do this by taking 4 different models. So the parameterization, the different colours, are unimportant. These models were all made using normal modes. They were all made for a uniform structure which varied with depth, but not with hemispheres. And clearly they are different to each other. In particular, some models expect very little anisotropy at the centre, and other models predict much greater structure at the centre. In fact, it was suggested that this structure here may be evidence of the innermost inner core. When we take these models and chop them in half, we can calculate the frequency of an oscillation and its quality factor, and that just tells us about how long a mode will keep on oscillating after an earthquake. So I'm showing you frequency and quality factor for the 4 different models. And you will see that the hemispheres are shown in red, and sometimes the hemispherical structure causes big differences. Sometimes these changes are in quality factor, sometimes these changes are in frequency, sometimes the changes are in one direction and sometimes they're in a different direction. There is no uniform response to putting hemispherical structure in the inner core. There is no one thing that this normal mode does. And in fact, different normal modes will do different things when you put this structure into the inner core. We can also look at spectra. We can look at the actual splitting of the peaks, and we see again that some normal modes have big changes in their amplitude, some have changes in the phase of oscillation, and sometimes we see very little differences whether we put hemispheres in or not. So the black I'm showing you data, red again is hemispheres, blue are no hemispheres, and the changes depend on what model you start with and which mode you look at. When we talk about body waves, we nearly always talk about P waves or compressional waves in the inner core. But some normal modes are not at all sensitive to VP in the inner core, but are sensitive to VS or shear velocity in the inner core. 6S3 is a mode which is sensitive to structure right throughout the Earth, but in the inner core, we have no sensitivity to VP, so we have no green line visible here. This mode doesn't care what sort of anisotropy we put in P wave velocity in the inner core, but it does notice what we do to shear wave velocity in the inner core. And again, the forward calculation tells us that if we put hemispherical anisotropy into the inner core, we see big differences. So these modes will be a good way for us to look for hemispherical shear wave anisotropy. If we can look at forward calculations of spectra, there is another, even better way to look at normal mode oscillations, and that's by using splitting functions. Splitting functions tell us how a mode is affected by depth average structure in the inner core. This splitting function is for a mantle-sensitive mode, and it tells us how the peaks for this mode are split across the Earth. So we see here structure which looks familiar when we think about deep Earth structure. This is structure from the mantle. We see around the edge of the Pacific these blue colours, where we know we have subduction and cold, fast plates. In the centre of the Pacific and under Africa in this mantle splitting function, we see red patches, and we know that in the mantle there we have superplumes. So these splitting functions tell us about depth average structure for which this mode is sensitive. So in this case, mantle structure. But if we look at a mode sensitive to the inner core, we see a different sort of picture. So this is the observation, and we see this stripe. We see blue colours at the poles and red colours at the equator. And if we predict what this splitting function would look like just with mantle structure, we see a very different pattern. But as soon as we put inner core anisotropy, uniform inner core anisotropy, into our prediction, we see a very good match. This is the characteristic of inner core anisotropy, this stripy pattern with opposite colours at the equator to at the poles. I've told you already that if we just look at one mode in an isolated self-coupling calculation, we're not sensitive to odd degree structure. But if we can look at a pair of modes and the splitting function of that pair, then we can look at odd structure. So we look at the cross-coupled splitting function of these two modes, 16s5 and 17s4. 16s5 is sensitive to velocity and density right throughout the Earth, but 17s4 is only sensitive to inner core structure. That means that if these two modes cross-couple, if they resonate, it has to be caused by structure in the inner core. Structure in other parts of the Earth will not allow these modes to interact. So we can make this splitting function observation, and we observe this distinct hemispherical pattern. So we have the west, which has opposite signature to the east. So where we have red in the west, we have blue in the east, and vice versa. And if we make a prediction without hemispheres in the inner core, we would predict nothing to be seen. But if we put hemispherical structure into the inner core, then all of a sudden we see a pattern similar to the observation we can make. And this is just an observation for one mode, but if we measure splitting functions for other normal modes, then again we start to see these hemispherical patterns in the odd degree splitting functions. So with normal modes, we can determine that coupling will affect modes sensitive to the inner core and allow us to see the hemispherical structure in the inner core, both in forward calculations of spectra and in observations of splitting functions. Finally, I just want to talk to you very quickly about the boundaries between the two inner core hemispheres, because the number of seismometers we have, especially in places like Europe, are growing very rapidly. So I'm showing you here data from one earthquake in Tonga, recorded all across Europe. And there are triangles where each wave gets to its deepest part in the inner core. Green will tell you where that wave is in the inner core. And you can see that we have a great deal of data now just from one earthquake. We can use this sort of data to make a cross-section through the inner core because there are so many waves which turn there. So what I'm showing you here are the travel time anomalies. So red colours tell us that the inner core is faster than expected. Blue colours tell us that the inner core is slower than expected. And all these measurements have been corrected for what we know about the mantle. So they're only telling us about structure in the inner core. And you can see that for this whole cross-section, which goes from under Indonesia all the way up to Canada, we see changes in the travel times, but a fairly smooth structure here. There are no big, sharp changes until we get suddenly to this point in the cross-section. And suddenly we get this huge blue patch. We get slow travel times at this end of the cross-section. And these slow travel times correspond to the Western Hemisphere. And the boundary I've already calculated for the Western Hemisphere is shown here. So clearly for these data, there is a sharp difference between being in the Eastern Hemisphere and being in the Western Hemisphere. We see sudden change in the colour of these triangles, which corresponds to a sudden change in the differential travel times we measure. So it looks for these data like there is quite a sharp difference between the Eastern and Western Hemisphere. A completely different study, which has been led by Lauren Vacek, who's also at the University of Cambridge, looked at the very top of the outer core. So she used different seismic waves. She used PK as a reference wave, and that's a wave which gets to the outer core boundary and then bounces back off. And again, she finds these very sharp hemisphere boundaries. So at different depths, she finds boundaries here, and here, and here. And the first thing you see is that there's really quite a sharp difference between the Eastern Hemisphere and the Western Hemisphere. The other thing you will notice is that these boundaries move ever so slightly as you look deeper into the inner core. And this may be evidence of a very, very, very slow inner core rotation. So the estimation is that it's maybe of the order of 0.1 or 1 degree per million years. This is significantly slower, 1 million times slower than previous estimations of inner core rotation. And obviously there is quite a lot of uncertainty on this figure because we don't know things like the growth rate of the inner core very well. So this figure could be lower, it could be higher, but of the order of 1 degree per million year rotation. At least the evidence from the top 90 kilometres of the inner core. Annie has already mentioned different causes for the hemispherical structure, but briefly they can be divided into 3 different sorts. So we have possible thermal causes, and this is work that maybe Julien will talk about later today, but if we have different thermal gradients in the outer core, we may then find that we have different sorts of growth on the inner core boundary. Alternatively, we could think about magnetic gradients causing the hemispherical structure, and I show here the magnetic field with the north-south component removed. So we normally expect the magnetic field to have very strong north versus south difference. That's what we see on a magnet. If we take away that structure, we see that the Eastern Hemisphere magnetic field has stronger flux than the Western Hemisphere magnetic field. Now, I don't know why this could cause hemispherical structure, but clearly if we have a difference in the magnetic field between the East and West Hemisphere, even though it's just a small one, that may in some way be linked to the seismic observations we can make. And then, of course, the final suggestion has to be the inner core translation that Annie has already talked about today, where we have the whole inner core sliding sideways, although it's not hugely clear to me how this sort of structure could explain the sharp boundaries, but this is still a good suggestion on how we could explain the differences between East and West. So to conclude, we see 2 distinct hemispheres of the inner core, an Eastern Hemisphere and a Western Hemisphere. We have now 2 completely different sorts of seismic data, body waves and normal modes, which can see this structure. Either thermal or magnetic structures may cause the differences between the properties we can observe, and as well as these big hemispheres, we can start to see smaller details like the sharp boundary between the 2 hemispheres using seismic body waves. Thank you.